Hello everyone. So let's start today's class. Today we will see some phenomena as well as some applications. So let's start from optical fiber. Optical fiber. So I am drawing first diagram. You just see how it will be. You can see here. This is how transmission takes place through this optical fiber. Like this. Now this phenomena or this optical fiber works on the principle of total internal reflection, we can say. The first point I am writing here, works on the principle or you can write like this, that is phenomena also. Works on the phenomena of total internal reflection. Okay. Next. Now here inside part and outside part is there. This inside part is called core. Okay. What is this? Core. And it has high refractive index. Next one, this part, which is outer side one, that is called cladding. And it has low refractive index. Low refractive index. Okay. Now this diameter is there. No, this diameter is how much? 10 power minus 4 centimeter diameter. This is there. No, its diameter is how much? 10 power minus 4 centimeter. Right. So light incident on this will always follow the zigzag path because of total internal reflection. And you know, total internal reflection means when it takes place, when angle of incidence is greater than critical angle. That is, I am writing here, angle of incidence should be greater than critical angle. That is what principle we can say of total internal reflection. So like that data will transmit. So what are the applications of this optical fiber? So here I am writing applications of this optical fiber. Number one, in endoscopy. So this endoscopy is what? What is endoscopy? Examination of even what we can say inaccessible parts of human body. That is called endoscopy. So this is what first application. Second application of this is transmissions of electrical signals. Transmission of electrical signals. And third application, that is telephone and other transmitting cables. You know, that is what our data lines we can say. We are getting internet, no? That is also with the help of this optical fiber. Telephone and other transmitting cables. These are the applications of this optical fiber. So it has core, cladding, inside part high refractive index, outside part low refractive index. Diameter is nearly 10 power minus 4 centimeter. And it works on the principle of total internal reflection. Okay. Next. Now, what is scattering of light? Next one is what? Scattering of light. Scattering of light. So what is this? If someone will ask you what is scattering of light, here I am writing definition. So atoms or molecules, atoms or molecules. First, I will tell in one line what is scattering of light. Absorption and re-emission of light. What is that? Absorption and re-emission of light. That is what your scattering of light is. Now, let's see what I am writing the definition. Atoms or molecules which are exposed to light, which are exposed to light, exposed to light, absorb light energy, absorb light energy, and re-emit light in different direction with different intensity. Different directions with different intensity. This is what your scattering of light. What is this? Scattering of light. Who studied this first? This scattering of light first studied by Rayleigh. Scattering of light first studied by Rayleigh. That is scientist name, not Rayleigh. Okay, this is Rayleigh, scientist name. And according to this Rayleigh, A is equal to AV by R lambda square. What is this A? What is this AV and R lambda square? See here, where capital A is amplitude of incident light, next is lambda is wavelength of incident light. Yes, wavelength of incident light. Next this capital V, this one, okay, volume of scattered particle, volume of scattering particle, and small a is amplitude of scattered light. At a distance r from scattering particle. From scattering particle. So here if you will see in the formula, small a and capital A both are amplitude. Now see, first is A is what? Amplitude of incident light, capital A. Lambda is wavelength of incident light. Now volume of scattering particle, and A is amplitude of scattered light at a distance r from a scattering particle. Means what? I will show you one diagram, then you will understand clear. Let us suppose this is a light wave. Listen carefully how I am drawing for your understanding. This is a light wave. Okay. And now this is what your capital A of this incident light. This is amplitude. Now here you are having one particle. Let us suppose something like this. There is a particle. This is particle. Okay. This is amplitude of incident light. So let us suppose this is incident light. This is just general explanation for your understanding. Now this is a particle. So its volume is what here? This is volume P. P is a volume of this scattering particle, whatever it is. This is volume. Now after this light will get scattered in different directions. So let us suppose this light is getting scattered like this in different directions. Okay, like this. So at a distance r from this, so let us suppose at this distance r, whatever you are getting, the amplitude of this is r distance from this, and at this point whatever amplitude of light is there, that is your small a. This amplitude from this mean position, whatever this amplitude is there for this wave, that is what is which we are going to find. Understand from this formula. Is that clear? Yes, understood. Next one, you see now. According to this relay, what he is saying, intensity of scattered light. This is very important. Intensity of scattered light, that is IS, suppose IS stands for intensity of scattered light, is inversely proportional is inversely proportional to fourth power of wavelength. Okay, that is I is directly proportional to 1 by lambda power 4. 1 by lambda power 4. Actually, how you are getting this? See, basically, this IS is directly proportional to A square, that is amplitude square. Okay, of scattered light. A is what? Amplitude of scattered light. Amplitude of scattered light. And just now we have seen this relation, that is A is equal to AV by R lambda square. A is equal to AV by R lambda square. Now this A is amplitude of incident light, V is volume, and this R is all constant. So A is directly proportional to 1 by lambda square. Now if I want IS is directly proportional to A square, so that is equal to 1 by lambda power 4. This is what the relation which we are getting from this formula. Understand? The intensity of scattered light is directly proportional to amplitude square and inverse proportional to lambda power 4. Already I have mentioned what is this lambda. Lambda is what? Wavelength of incident light. Here also wavelength of incident light. Lambda is what? Wavelength of incident light. Okay, right? Understand? So, is there any application of this scattering of light? Yes, there are so many applications of this scattering of light. Okay, so let's see one by one. Let's see one by one. That is this applications of this scattering of light. Next one, applications of scattering of light. Listen one by one, then you will understand. Applications of scattering of light. Applications of scattering of light. Okay, let's start. First one, that is blues color of sky. Blue color of sky is also what we can say one application of this scattering of light. Next one, white color of clouds. Next one, the sun looks, already you know this all. The sun looks reddish at the time of sunset and sunrise. And next one, that is danger signals are red. So these are the applications of this scattering of light. Okay, understood? Okay, next, let's move ahead and see what is the rainbow. Okay, what is rainbow? Rainbow is what? It is a combined phenomena. Yes, what is rainbow? It is a combined phenomena of reflection, refraction, and total internal reflection. Reflection, refraction, and total internal reflection. Okay, so let's see how it is taking place. That is primary rainbow and secondary rainbow. So this is here I am writing primary rainbow, and here it is secondary rainbow. Now if I will draw the diagram, you will understand everything. Suppose this is a raindrop. Okay, this is a raindrop, and this is also raindrop here. See now what is happening. Now this is a sunlight which is entering. Can you see this sunlight? Yes, it is entering into the raindrop, and now it will get refracted. Little refraction takes place like this. And now this is denser medium, this is rarer medium. At particular angle, what happens? This ray will reflect back into the same medium. And what happens? Total reflection takes place here. And when these two rays are coming out, what is happening? First violet color is coming out. Yes. So here it is first violet color, and next is red color. So in between all colors will be existing here. And here is observer. If suppose this is a eye, then with this observer, what is the angle made? This angle is 40 degree. How much this angle is? 40 degree, and this angle is 42 degree. Okay. And what is this color is? Violet, and this color is red. In between this, all colors are going to exist. That is what your rainbow is. So how many times total internal reflection takes place here? One time. So I am writing one more point here. Only one total internal reflection takes place, and colors are from phi to red, and colors intensity is dark. Intensity is dark. Okay. Next one, you see in this secondary rainbow, what happens when this light enters into this raindrop, somehow like this. Then first refraction takes place, and at this point first internal reflection takes place. Again at this point another total internal reflection takes place here. Okay, and then from here rays will come out. So first is coming like this, red one, and another one is violet. So it is coming something like this. And here is your observer. And at this, what are the angles made? With this it is 53 degree violet color, and this is red color. So it is making 50 degree, and here is your observer. Okay, so how many times total internal reflection takes place here? Two times. Yes or not? How many times? Two times. So I am adding here point. You can see two times total internal reflection takes place. Colors are from red to violet. Red to violet, and intensity of color is faint. Intensity of color is faint in this secondary rainbow. Okay, in this secondary rainbow. You can write here, this is red color. Yes, and this is violet. Red to violet colors. Understand? This is what your rainbow is. Right? Okay. Next is Mirage. Now see, let us assume that there is a person who is standing over here, and here is a tree, Now see here, I'm showing you some part. You can see I'm showing with the different colors what actually happening here in hot summer days. What happens, you see, just so now in summer days particularly, this air is how This air is very hot air. This air is hot air. So as this is hot air, its refractive index is less mu, and behaves as a how rarer medium. Behaves as a rarer medium. Now as you are going up and up, no, this is rarer medium. Yes. Now here it is hot. As you are going up and up, it will be cool air. It will be cool air. So this one is cool air. Cool air. So it has little bit high refractive index, high mu, and that's why it will behave as a denser medium. How it will behave as a denser medium. So now when light enters, suppose from this top of the tree, light is going to enter like this, somewhat like this it enters. Okay, I will take a straight line. Now can you see this is a light is entering into from this rarer to denser medium. Assume करो ऊपर भी denser medium है, right? So complete. So light is entering like this, and then what happens at particular angle here at this point? At this point, what happens? Total internal reflection takes place, and this light will reflect into the same medium, and it will enter into the person's eye. Okay, what happened? Yes, can you see? Light is going to enter into the same medium. Now, as this light is going to enter into the same medium, what this person will feel that this light is coming from somewhere here. Okay, how it is coming? From somewhere from here like this, instead of coming up. And that's why this tree, it will appear inverted, and this is what phenomena of mirage we can see. This is what phenomena of mirage. This one is appearance only. This is optical illusion. What is this mirage means? This is just an optical illusion. Keep it in mind. That's why I am indicating with dot lines. So this light is actually coming like this, but it appears how like this. And this image is also like that only. This image is also just an illusion, not reality. That's why you can draw it dotted lines, or you can keep as it is, not an issue. Okay. So mirage is what? Optical illusion. Optical illusion. Yes. In hot summer days. In hot summer days, what happens? Air near the surface, it is hot air. Above there is cool air. So it behaves as a rarer medium. It behaves as a denser medium. When light travels from denser to rarer, total internal reflection takes place due to total internal reflection, and hence surrounding object appears. Surrounding object appears inverted. Surrounding object appears inverted. Understand? Okay. So let's stop here for today. Read carefully now. Bye.